Welcome to the next video in the series on condensed matter theory. In this video I want to talk about Thomas Fermi theory, which defines a practical functional to go from density to energy. And actually Thomas Fermi theory predates the Honenberg-Kohn theorems by 20 years or so. But this is a nice functional that fits into the realm of this theory. Thomas Fermi theory does not give very accurate results, but it gives you an idea on how we can define functionals, and we can see how we can improve upon those functionals then in the next video. And we see what actually is missing and where we have to put more attention. So when we look at the energy, we will write the energy as a sum of the kinetic energy, the potential energy, and the Coulomb energy. And we will again use the letters for either the operators or the expectation values as used in the density functional theory community: T for kinetic, V for potential, and U for Coulomb. The potential energy is easy to calculate from the electron density, and that is V times rho of R integrated over R. Thomas and Fermi used the classical approximation for the Coulomb energy. So we have 1 over 4 pi epsilon 0, if you work in SI units, E square over 2. And then the double integral, rho of R prime, divided by R minus R prime. And the norm, dr prime. So what is missing here is definitely the exchange part of the energy. But also, well, the correlations are slightly different because you have wave functions and fluctuations in there. And it's not just the density that would define this on this kind of formalism. Nonetheless, that is the approximation made in Thomas Fermi theory. Worse is the kinetic energy. And the kinetic energy is defined in quantum mechanics related to the wave vector of the wave. And of course we look at densities now, so we don't have wave functions and wave vectors anymore. So the question is really how to calculate the kinetic energy from a density only. And what Thomas and Fermi did is to look at the free homogeneous electron gas. So that is basically the Sommerfeld model. We can calculate the total energy at 0 Kelvin if we integrate from 0 to the Fermi energy, the energy times the densities of states, dE. So the question is, can we now find a function that expresses T in terms of the density? And for a homogeneous electron gas, we know that the density is just given by a constant. And we now have to write down the total energy, total kinetic energy, as a function of the electron density in our homogeneous electron gas. We can express the Fermi energy in terms of how many particles we have in our system. We did this when we introduced the Sommerfeld model, creating the Fermi sphere, calculate how many one-particle functions are in there. And then we can calculate the Fermi wave vector or the Fermi energy as a function of number of particles. And for the energy, this was n to the power 3/2, 3 pi squared to the power 3/2, h bar square over 2m. And the densities of states for our free electron gas is a square root of the energy with a beautiful prefactor 2m over h bar squared, 1 over 2 pi squared, and this to the power 3/2 square root of E. Such that the kinetic energy is the integral 1 over pi squared, h bar squared over 10 times the mass of the electron, 3 pi to the power 5/3, and then the density of the electrons r to the power 5/3, and then the integral over the whole space. We have the energy times density of the energy is the power 3/2. Yeah. So we have for the free electron gas a function of the kinetic energy as a function of the density. Of course, there it's a function because the density is a constant, but what Thomas and Fermi did is use the kinetic energy now not only for constant densities but also for densities that are varying. So we're going to extend this and use it also for cases where the density is not just a constant. So we can also understand where we need to improve when we look at Thomas-Fermi theory. And the first part where we really need to prove is in the terms of the kinetic energy, because, well, here in principle we have a Hartree approximation for the Coulomb interaction. We can improve from Hartree to Hartree-Fock. But the kinetic energy is even worse than in the Hartree approximation, and that is really where we have to improve. So how can we correct the kinetic energy, and how can we improve and add also the exchange energy to the Coulomb interaction? And that is something that we will discuss in the next video. For now, thank you for your attention and stay healthy.